Hi students, welcome to Sunil Engineering Academy. I am Sunil. In this class, we are going to learn Power Systems Class 3. Power Systems Class 3. We have already completed two classes in Power Systems for RRB JE or SSC JE or other competitive level examinations like another JE level or AE level examinations. Okay, this is my official website, that is www.sunilengineeringacademy.com. Okay, and if you want any PDF, that is for RRB JE or NTPC or SSC JE, you can download the PDF from our official website, that is www.sunilengineeringacademy.com. This is my official mail ID, that is our channel mail ID, chelpline@gmail.com. Okay, if you want any PDF, download from this website, friends. Okay, we have already completed two classes. This is the third one in Power Systems. If you want access my live classes, I am taking the live classes in Unacademy Plus platform. Unacademy Plus platform, I am taking live classes. If you want access those, get subscription under railway examinations in Unacademy. In unacademy.com, www.unacademy.com, or open the Unacademy Learning app. In that, get subscription under railway examinations with using the referral code Sunil sir. If you use the referral code, you will get 10% discount on that. Okay, 10% discount on that. Here you will get interaction, friends. These are live classes. Live classes. You will get interaction between student and educator. If you miss any class, you can also watch as the recorded one. This course will be very useful for your preparation. Okay, let us moving into the class. We have discussed already, there is generating stations and economical operations. Now we are moving to another topic, that is transmission and distribution. Transmission and distribution. We know the total transmission and distribution. Here we have generated the voltage nearly, let us take 11 kilovolts. We are mainly or generally generated 11 kilovolts, and this 11 kilovolts will be stepped up and this will be transmitted through this transmission lines. After that we have to step down the voltages, and then distribute them to the load. Here why we need to step up and then step down? Okay, can we transmit with 11 kilovolts? Can we transmit with 11 kilovolts? Then what happen? Then what will be happen, friends? For example, if we transmit with low voltage, that is generating voltage, there is a with low voltage, we know that power is equal to root 3 VL IL cos pi, VL IL cos pi. That means for same constant power, what will happen? This IL value is equal to P by root 3 VL cos pi. Okay, from this equation we will get this one. Here the power is constant, and we don't know the load. Then this IL is inversely proportional with voltage na, that means if we transmit with low voltage, we have to transmit with higher amount of current, that means current value will be high. As current value will be high, as IL will be high, then I square R loss will be high. Then the losses will be high, means the efficiency value will be decreases. And we know that the conductor area of the cross section of the conductor is proportional to the load current, If IL is higher, means the area of the conductor must be high. For that we have to, the cost will be high. So due to these disadvantages, we are step up the voltage to higher level and we have to transmit it. After that we are using distribution, and for this purpose we are using the transformers. Friends, transformers. Okay, here just wait. Yeah. And so here what are the main primary lines in case of transmission system? Presently the highest voltage, the highest transmission voltage in India is 765 kilovolts friends, 765 kilovolts, and second 765 kilovolts. We can say that we have two transmission lines. We can divide the transmission line into two, primary transmission lines and secondary transmission lines. After that, primary distribution and secondary distribution. Okay, secondary distribution. And here in the distribution lines, we have these are divided into feeders, distributors and servicemen. Feeders, distributors and servicemen. First of all, coming to the feeders, what are the important point in this feeders? The main important point in this feeder, it does not contain any tappings friends. It does not contain any tappings. Why? Because these are designed based on current carrying capacity. The current is same. Current is same in case of feeders. Okay, that's why we will not provide any tappings to maintain the constant current. Here very important bit. Feeders are designed based on current carrying capacity. And distributors are designed based on voltage drop friends. It is the most important one, voltage drop. And the limit of voltage variations at the customer side, that is plus or minus 6% friends, plus or minus 6%. As per IE rules, plus or minus 3% in case of that is urban areas, plus or minus 6% in case of rural areas. You have to choose the plus or minus 6% in the option. They will give either 6 or either 3. Only they will give one option. You have to choose plus or minus 6%. Okay. If plus or minus 6% is not there, if we have only plus or minus 3%, you have to choose the plus or minus 3%. Okay. And here I have given the what is the need of high voltage. What is the need of high voltage? Here as the if the voltage is increases, if for same power, we know that power P is equal to root 3 VL IL cos phi. For the same power, that is VL value is high, then current value will be low. So as the current is decreases, then size of the conductor reduces. As current decreases, I square R loss also decreases. So as loss decreases, efficiency will be increases. Okay. And another important one in this, effect of voltage on feeders and distributors. How the voltage effect on feeders and distributors? For example, let us take the feeders. For same power, same length, same material, if the voltage increased by n times, that is, we can take the initial case V1, I1 and R1 and final case values V2, I2, R2, and what they are giving, voltage increased by n times. That is, let us take V2 is equal to n into V1. Can take this, V voltage is increased by n times, so we can say that the final case, that is V2 is equal to n into V1. So I am taking this, and here they are given same power, so S1 is equal to S2, that is apparent powers is equal to equal, that is V1 I1 is equal to V2 I2. Then we have to substitute in the place of V2, we have to substitute nV1. So we will get nV1. From this we can say that if V1 and V1 is cancelled out, then I1 or I2 is equal to 1 by n into I1. I2 is equal to 1 by n into I1. So we will get I2 is equal to 1 by n into I1. That means the current value decreases by 1 by n times. The current value is decreased by 1 by n times. So we can say that as voltage increased by n times, then current value decreased by 1 by n times. That is the most important one. So if the current, we know that if the current is reduced by 1 by n times, here the current, we know that current is that is area of the cable is proportional to the current area of the cable, that is cross section area of the conductor is proportional to current So here as current increases, the area of the conductor also increases. Okay, that means here the area, the current will be reduces to n times. current will be reduced to n times, then area also reduces to n times. So area also reduces to 1 by n times, friends, 1 by n times. Okay, and 1 by n times. In case of distributor, what happened if the voltage increases by n times? If the voltage increases by n times, let us take initial case and final case. Here in this final case, what will happen? Here voltage value increases by n times na, and here we have to consider, in case of distributor, we have to consider voltage drops, friends, voltage drop, that is per unit voltage drops are same. What is the per unit voltage drop? IR by V is the per unit voltage drop, let us take the initial case I1 R1 by V1, for final case I2 R2 by V2. So I am equating these two, so we have V2 is equal to n into V1. Substitute that, you will get, in the place of V2, substitute the n into V1, here V1 and V1 cancel, then we will get I2 R2 is equal to this value is equal to this n into I1 R1. So I got the same. That means the voltage drops, I into R means nothing but voltage drop, V is equal to IR. I into R is nothing but voltage drop. Here voltage drop is increases by n times. So as voltage increases n times, then voltage drop increases by n times. And if the power is same, if we replace with V2 is equal to n into V1, V1 and V1 cancel, then you can say that current value reduces to n times, that is 1 by n times, 1 by n into I1, that is reduced to 1 by n times. If the current is reduced to 1 by n times, then what are the voltage drops? Here they are given I2 R2 is equal to n into I1 R1. We got this one. I2 R2 is equal to n into I1 R1. So from this, if substitute this I2 value here, that is 1 by n into I1, then we will get R2 is equal to n square into R1, that is resistance increased by n square. We know that R is equal to rho L by A. If the resistance increases, then area of the cross section is decreases na. So here area of the cross section is decreases by 1 by n square times, so it is very important one, friends, very important. Okay, so finally we can say that in case of feeders, as voltage increases n times, the current decreases to 1 by n times and area also decreases to 1 by n times. But in case of distributor, current is reduced to 1 by n times and area is reduced to 1 by n square times, Okay, this is one we have to remember. And what are the standard voltages in India? 11 kilovolts, 22, 33, 66, 132, 220, 400 and 765. These are 400 or 440 are the standard voltages in India. It is the highest one. Okay. And why all are in the factor of 11? Why? Because if we send 11 kilovolts, then there are losses in the system, so we will get the voltage 10 kilovolts. If you send 22, we will get 20 kilovolts, like that. For this purpose, to meet the losses, they are designed like that, friends. Okay. And the next one, classification of transmission lines. These are also important. Here in case of short transmission lines, the length is less than 80 kilometer. Here length is very less, so we can neglect the capacitance effect. Okay. And these are studied by lumped model. And another one, second one, that is maximum transmission lines. Here the length of this maximum transmission line is 80 to 160 kilometer, friends, 80 to 160 kilometer. Here length is higher na, so the capacitance effect, that is conductor between the earth, will be increases. So we have to consider the capacitance effect in case of medium transmission lines, in case of long transmission line also. Okay. And here the modeling, these are modeled by with which model? These are modeled by which methods? These are the important. In case of short, they are modeled by lumped model. In case of medium transmission lines, they are modeled by nominal T, nominal pi method. In case of long transmission line, the length is greater than 160 kilometer and they are modeled by using equivalent T and equivalent pi methods. Okay. Friends, we have very less time, that's why I am giving just brief idea. This is not copied paste material, friends. This is by hand, this is handwritten notes, this is prepared by me. I am preparing this material by using by the source of different textbooks and different coaching center materials and by adding the some of the important bits from previous papers. Okay, okay. I am not just reading, friends. Okay, because there is a very less time, so we have to cover more topics, we have to gain more score, that is the important one, that is the important one. Okay, here the next one, regulation in transmission lines, that is voltage regulation, that is the difference of sending end voltage and receiving end voltage with respect to the receiving end voltage, nothing but you can say that voltage regulation. This voltage regulation for lagging power factor, it is plus, friends, IR cos pi r plus IXL sin pi r by VR. For leading power factor, it is minus. It is minus, friends. Okay. For example, if you take short transmission lines, the voltage regulation value for lagging power factors. That means we know that all the loads are maximum lagging power factor. Why? Because all are inductive loads, na? Inductive loads. So we will get lagging power factor. Here from this we can say that here let us take this VR. Okay, here current is lagging, na? Current is lagging. So we can say that here the horizontal component IR into R, vertical component IR into X, the resultant will be Vs. The resultant will be Vs. Okay, the resultant will be Vs. So we can say that Vs is equal to VR plus IR into R, Ix, that is IR into X. Okay, here horizontal component is IR into R cos pi R, IR into X sin pi R. From this we can easily say that Vs minus Vr is equal to this one, and here if you take this with voltage regulation, we have to divide with receiving end voltage, we will get this one, that is voltage regulation. Here this is per unit value, so we can say that R per unit cos pi r, here X per unit cos pi r, S per unit cos pi r. Here what are the important one in this voltage regulation? That is condition for maximum regulation and condition for minimum regulation. These are the important one, friends. Here condition for maximum regulation. Here the regulation curve is like this. Okay. Here unity power factor. Here this is lagging, this is leading. That means we have got higher voltage regulation at this lagging power factor and zero regulation at leading power factor. These two are very, very important. We got higher, that is maximum regulation at lagging power factor, zero regulation or minimum regulation at leading power factor. And at unity power factor, what is the regulation? Unity power factor, that is percentage R per unit, Okay. Here the maximum voltage regulation occurs in lagging power factors, and when it will be occurs, we have three conditions. Whenever it satisfies any of these conditions, we will get maximum regulation. That is here tan pi r is equal to x by r of the load, x by r of the transmission line, x by r of the transmission line, or theta is equal to pi r, that is impedance angle is equal to pi r. Impedance angle is equal to pi r. Pi r is nothing but the phase angle, that is phase angle between this IR and this VR and IR. Okay. And one more, x by r of the load is equal to x by r of the transmission line, then also we will get the maximum regulation. And here the two important points, the maximum regulation value is percentage Z or Z per unit. Here voltage regulation at unity power factor is percentage R, that is R per unit. In the exams they will give only percentage R value and ask for the voltage regulation at unity power factor. If percentage R is equal, they will give 5 per unit, then voltage regulation also 5. Okay, like that. Okay. And the next one, minimum regulation. These are somewhat different, that is somewhat opposite that of maximum voltage regulation. Okay. Here the first one. Here tan pi r is equal to x by r of the transmission load. Here r by x of the transmission line. Here pi is equal to, that is theta equal to pi r. Here theta plus pi r is equal to 90 degrees. Here x by r of the load is equal to x by r of the transmission line. Here x by r of the load is equal to r by x of the transmission lines. You have to remember all this. Okay. And medium transmission line, how they are modeled, that is by using end condenser method, and nominal T method and nominal pi method. Here the important ones are ABCD parameters. We are modeling with ABCD parameters. We know that transmission lines are modeled by using ABCD parameters, that is VS, IS, sending end voltages. VS is equal to AVR plus BIR, IS is equal to CVR plus DIR. Okay, if you do the derivation, then we will get ABCD is equal to 1 plus YZ, ZY1, ZY1. For this, I have one important trick to calculate this ABCD parameters. For example, whenever the transmission line models as like this, that is, let us take impedance Z. Then the ABCD parameters are 1, second one Z, 0, 1. In this way we have to model ABCD parameters. Okay, if it is Z like this, the modeling is 1 Z 0 1. For example, if it is like this, then the modeling ABCD parameters are 1 0 Y 1. If it is Y, 1 0 Y 1. For example, if it is Z, we have to take in the place of Y 1 by Z. That means we will get for this one 1 0 1 by Z 1. Okay, 1. So for this, to modeling this is all the derivation part. This is somewhat difficult. Just remember it is R plus X, that means Z. Here it is Y. Parallel means we have to consider admittance. Series means we have to consider Z. For this model, calculate for this model. What is the ABCD parameters? 1 Z 0 1 1 Z 0 1 like this. 1 Z 0 1. For this part, this is parallel. So parallel means 1 0 Y 1. 1 0 Y 1. So we have to multiply these two. That means the we have to multiply these two. That means here the ABCD parameters, when they are connected like this, they are multiplied, friends. If we multiply these two, we will get the same ABCD parameters. Okay, same ABCD parameters. Here one of the important point, here by using this end condenser method, here A is not equal to D. That means it is not obeys the transmission line property. So we will not use this end condenser method for modeling. That's why we will not use the end condenser method for modeling, friends. And the next one, nominal T model. Yeah, nominal T model. Here in this nominal T model, this is the shape is like this, friends. That is, they are modeled like this in the T shape. That means here they are taking R by 2 and X by 2. Here they are taking R by 2 and X by 2. Here they are taking the capacitance. That means R by 2 plus Jx by 2 is nothing but we can say that Z by 2. Here also they are taking Z by 2. Here Y. Here they are taking Y. Okay, how to model this? Just simple, friends. By the formulas that is difficult, by using the this trick you can easily solve this. For this one, 1 Z by 2 0 1. For this one, that is parallel one, 1 Y 0 1. For this one, 1 Z by 2 0 1. If you multiply this matrix, you will get the ABCD parameters. That is, A equal to 1 plus YZ by 2, B is equal to Z into 1 plus YZ by 4, and C is Y, and D is equal to 1 plus YZ by 2. From these two, A is equal to D, A is equal to C, A is equal to D. So we can say that it is a symmetry. And AD minus BC is also 1. So we will get We can say that it is passive. Okay. Here nominal pi method. In this nominal pi method, they are taking, we have to take like this pi in the shape of pi. Here what is this? Here they are taking c by 2 c by 2. So we are taking y by 2 y by 2. Here they are taking z. So we are taking z. Okay. So for this one we have to write the ABCD parameters 1 1 0 y1. Y means here we are taking y by 2 1, and for this one 1 z 0 1. For this one 1 0 y by 2 1. Okay, if you multiply this you will get, the ABCD parameters. Okay, in the exams they will ask that in case of nominal pi method, what is the value of b, or what is the value of a, what is the value of c, what is the value of d. Like that you may get to chance to ask the question in case of competitive exams. In IES these are very important. Okay. And the next one, various transmission systems. These are not much very important. These are, let us take DC systems and DC single wire, two wire system, three wire system, AC systems, that is two wire systems, and midpoint converters. These are here the most important ones are that is the volume of conductor material required. That is the important one, the volume of the conductor material required. Okay. Okay, in the PDF you will get all this, don't worry about that. Okay, and empirical formula, this may be not important. Okay, and transmission line parameters, these are very important. Transmission line parameters, that is RLC. We know that R is nothing but rho L by A. Here we are to consider the total length, so that is units are ohm per kilometers. Okay. And inductance is nothing but flux linkages by current through the conductor. And here if you want to find out the inductor between the conductors, that is in case of overhead transmission lines, the inductance in conductors, here no need to remember all these friends, you have to remember only the final formula, that is inductance in case of single phase or single conductor. For example, let us take A and B. You have to remember LA is equal to 2 into 10 power minus 7 ln of d by r dash. Here r dash is nothing but 0.7788 r. Here r dash is nothing but effective radius. Friends. Effective radius. Here d is nothing but spacing between the conductors. You have to remember only this. Okay. And r dash is equal to 0.7788 r. How it got? You can go through these derivations. Okay, and for in case of loop inductance, for total loop, if you take two conductors A, B, for this total loop inductance, you have to consider if the two are identical conductors, then we can say that LA plus LB, that is LB is equal to LA, or LA equal to LB in case of the two conductors are identical. Then we can say that it is 2LA, then we will get 4 into 10 power minus 7 ln of d by r dash. But in case of this three-phase system, D is replaced with GMD, R dash is replaced with GMR. But here GMR is nothing but R dash, friends. GMR is nothing but R dash only. And GMD is nothing but geometrical mean distance. First of all, what is this GMR? GMR is nothing but geometrical mean radius, and it is used to calculate the self-inductance. This is the GMR, that is R dash. Here R dash is nothing but 0.7788 R, and it is the R dash is nothing but effective radius. Here what is this GMD? Geometrical mean distance. For example, if you take the P conductor, this is the geometrical mean of the distance between P2 conductor 1, P2 conductor 2, P2 conductor 3, and P2 conductor 4, and so on. That means geometrical. For example, if you take three conductors 1, 2, 3, then it will be a distance of S1, S2, S3 like that. That is 3th root of the distance between P to 1. That is, let us take S1, P to 2, that is, let us take S2, and P to 3, let us take S3. Then it is S1, S2, S3. That means geometrical mean of the distances from conductor. Okay. In the exams, we will get two types of problems. These are very easy and very important. For example, in case of symmetrical and equally spaced lines, when they are divided, that is, the spacing is 4 meters in each conductor. They are symmetrical and also equally spaced with 4 meters. Then what is the GMD? GMD is equal to how many conductors we are? In the place of n, we have to take 3 conductors. So 3, and the distances here 4 meter, here 4 meter, here 4 meter. We have to take 4, 4, 4. So we will get 4 meter. But in case of all the 3 conductors in same plane like this, then what is the spacing? Here 4, here 4, and from A to C, here it is 8. So we have to take cube root of the distance between A and B, 4, and the distance between B and C, that is 4, and the distance between A and C, that is 8. So we have to take like this. Okay, in that way we have to calculate. And the next one, what is the bundle conductor system? Bundle conductor means if you take one phase, we have 2 conductors, or if you take one phase, we have 3 conductors. It is 3 conductor bundle system. It is 2 conductor bundle system. Here what we will get extra one? Okay, in single conductor system for 3 phase, we have only 3 phases. R, Y, B. In each phase we have only 1 conductors. But here in this bundle conductor system, we have 2 conductors for R phase, 2 for Y, 2 for B. That means total 6 conductors. And here in one phase we have 2 conductor, means we have self inductance between these two. We have self inductance, so we have self GMD between these two. We have self GMD between these two. So we have to replace this GMR with self GMD, Okay, so the formula will be for inductance, that is 2 into 10 power minus 7 ln of GMD by, actually it is GMD by GMR for 3 phase single conductor system, but in case of this bundle conductor, it is GMD by self GMD. Here what is this self GMD? Here the self GMD, it is the GMD of the self, that is for self, that is for one phase. Here we have 2 conductors, one phase. So we have also the GMD between these 2 conductors. So that is, we have to consider the spacing between these 2 conductors also. If the spacing is, let us take S, then here the self GMD value is equal to R1 dash into S. Here R1 dash or R dash is nothing but 0.7788 R. Okay, 7788 R. Let us take a simple problem on this, then you will get understand. Here the phases, the distance between the phases is given 8 meters and 8 meters, and the distance between the two conductors is 40. That means it is spacing S, and this is the distance D. Okay, between the two phases. Here what is the GMD? You know that GMD is nothing but, if we have 3 conductors, cube root of distance between the conductors, system. Conductor system means distance between the phases. We have 8 meters. From these two we have 8 meters. From these two, R and B, that is 8 plus 8, that is 16. So we will get the GMD. Then what is the self GMD? In the self GMD, we have to consider the spacing between these 2 conductors also. What is the spacing given? 40 centimeters. So we have root of R dash into S. We know that R dash, that is 0.7788 into R. R is given, that is 2 centimeters. So we have to take 2 centimeter, and spacing between these 2 conductors is 40. So we have to take 40. Then we will get self GMD. So from this from this what we can conclude? What we can conclude? Just wait. What we can conclude? From this example, we got GMD value like this. GMD value like this, that is 10, and self GMD value is that is nearly equal to 8, and R dash value is equal to 0, that is 1.57. Okay, we know that R dash is nothing but GMR. GMR is nothing but R dash. This value is 1.5, and self GMD value we got nearly 8. That means self GMD value is higher than that of this GMR na. Self GMD is higher than that of in GMR na. Okay, higher than this GMR na. In case of three phase system, the electric field intensity is V by GMR ln of GMD by GMR. But in case of bundle conductor system, we have to replace this GMR with self GMD. Here what we got the self GMD, it is higher. So self GMD is higher means here what is the electric field intensity? Decreases. That is voltage gradient also decreases. Okay, whenever this voltage gradient or electric field intensity decreases, then corona loss will be decreases. For that purpose, that is to reduce the corona loss. We are using bundle conductor system. How they are reduce the corona loss means here we are considering the two conductors for phase system. So due to this self GMD value introduced, the self GMD value is higher than this that of GMR value. So this denominator is higher means the electric field intensity is decreases, then the corona loss will be decreases. That's the way we have to understand. Okay. And the next one, what are the advantages of this bundle conductor system? Here as self GMD increases, E is decreases means corona loss will be decreases, that is voltage gradients also decreases. Okay, and if the losses decreases, efficiency is higher, and as self GMD increases, what happened to inductance? Here self GMD is increases, what happened to inductor? That value will be decreases. And we have the formula for capacitance also. Here in this capacitance, that is 1 by ln of, that is capacitance is inversely proportional to ln of GMD by self GMD. Here self GMD increases means this total part, this total term, that is ln of term will be decreases. This denominator, total denominator decreases means the capacitance is increases. So we can say that due to this bundle conductor, inductance decreases, capacitance increases. That means voltage profile improves. And another important topic, that is transposition of overhead transmission lines. Why we need to transposition? In case of transmission lines, there will be interference with communication lines, friends. There may be interference for communication lines due to this overhead transmission lines. To avoid that interference, we are transpose the overhead transmission line like this. If R phase is transposed like this, after that transposed like this, after that we will get transposed like this, then finally we will get the same phase R. Here for this Y like this we can transpose. After that we will get Y, and for B we will get we have to transpose like this. After this we will get B. That means finally we will get the same. Here what happened due to this transposition? Here actually in case of overhead transmission lines, for entire length it is very difficult to maintain the equal space between the conductors and height from the earth. It is very difficult to maintain the equal space between these phases and height from the earth. Okay, so that means the line parameters may not constant, that is L and C or R may not be constant. Okay. So due to that there may be a circulating currents exist. Due to that there is a interference for communication lines. To avoid this interference with communication lines, we are using transposition. But nowadays they are not using transposition. Why? Because there is no interference with communication lines. Why? Because the communication lines may not taken as overhead. Okay, most of the cases they are using in underground transmission lines by using the OFC, optical fiber cable. Okay, there is no interference with communication lines nowadays. So that's why we are not observing this transposition in present situation. Okay. And capacitance, the capacitance formula, we have to remember only the formula, the capacitance formula. Here the capacitance is equal to pi epsilon naught epsilon r by ln of d by r. That means the capacitance is inversely proportional with ln of d by r. Here the most important one, in the exam, the capacitance between phase to neutral, that is line to neutral, is 2 into the capacitance between the two lines. The capacitance between the two lines, that is the most important one. That is the capacitance between line to neutral. Line to neutral is double of that of capacitance between line to line. Capacitance between line to neutral is equal to 2 into capacitance between line to line. This is the most important one. From this we can say that the ratio of capacitance between that is line to line by line to neutral is equal to, if 2 goes to that side, that is 1 by 2. So the ratio of capacitance of line to line to neutral is 1 by 2. Okay, you have to remember only one thing, the capacitance between line to neutral is higher, that is 2 times of capacitance between line to line. Okay. And if in case of length increases, length of the transmission line increases, then what happens? We know that as length increases, R is equal to rho L by A. As length increases, the resistance also increases. And we know that here as length increases, the inductance also increases, then reactance also increases. As length increases, the capacitance value increases. As capacitance increases, then capacitive reactance will be decreases. For example, if the radius of the conductor increases, what will happen? If the radius of the conductor increases, then the resistance will be decreases. Here we know that L proportional to ln of d by r. Here R increases, that is denominator increases, inductor value will be decreases. Okay, and we know that C is inversely proportional to 1 by ln of d by r. Here radius increases, this total term decreases. This total term decreases, that is total denominator decreases, means the capacitance will be increases. And we know that inductance formula, that is ln of that is 2 into 10 power minus 7 ln of d by r dash. We can write this into like this, that is 1 by r dash minus 2 into 10 power minus 7 ln of 1 by d. For this we can write, it is 2 into 10 power minus 7 ln of d minus 2 into 10 power minus 7 ln of 1 by r dash. Can we write here? Can we write like this? That is ln of a by b equal to ln of a minus ln of b. Okay. So now I am writing 2 into 10 power minus 7 ln of 1 by d. If we want to write this d as 1 by d, we have to place minus. Okay. If I want to write this r1 in the numerator, I can take this plus. Then 2 into 10 power minus 7 ln of 1 by r or r dash. Okay. I am writing the same here. Here this 1 by r dash is nothing but belongs to self. Here it is due to the mutual. Okay. In the exams they will give the questions like that. In self inductance, it is only depends upon radius. It does not depend upon the spacing between the conductors. Okay, that means they will give the if the spacing between the conductors is increases, then what happened to self inductance? There is no change, friends. There is no change. Okay, like that we have to analyze. We have to analyze. Okay, and another one, internal flux linkages. These are internal flux linkages. Sorry, these are internal flux linkages. This is external flux linkages. That means the internal flux linkage may not have any radius term and spacing between the conductors term. That means if the radius increases or decreases, or spacing between the conductors increases or decreases, there is no change in internal flux linkages. That is internal inductance may not change. Okay, that is the important one. I have given all the details in step by step. Don't worry, download the PDF and you can get the idea on these topics. Okay friends, in this class we have covered transmission line parameters and basics of transmission and distribution. Okay, this PDF will be very useful for your preparation, friends. This is useful for all the JE level and also B.TECH level exams also. If you want live classes and more detailed explanation, you can join in the Plus course. In that I have discussed in detailed manner and we have very less amount of time. Okay, so that's why don't waste your time and download the PDF from sunilengineeringacademy.com. There is very nominal price, friends. That will be very useful for your preparation. Okay, and download the PDF and start your preparation. Okay, friends, and also please share this information to all your friends and please share this video. Thank you very much. Okay, this is my official website, that is sunilengineeringacademy.com. Thank you very much, friends. All the best for your exams. Don't waste time, friends. Okay, thank you.